Hi, my name is Christine Fritsch and I will introduce you to our paper Solving Hard Variants of Database Schema Matching on Quantum Computers. With quantum computers now available as cloud services, there is a global quest for applications where quantum advantage can be shown. Naturally, data management would be a candidate domain. However, workable solutions still require the design of hybrid quantum algorithms, since normal database problems cannot be solved on a quantum computer without a middleman. This demo will illustrate such an end-to-end solution, especially targeting NP-hard variants, since normal variants could be also solved on classical computers. We allow our participants to explore the critical design decisions, such as the handover between phases of QPU and CPU-based computation, and it will also allow them to experience how easily problem sizes exceeds the limitations of today's QPUs. In our Jupyter Notebook, the participants can edit all the inputs and check themselves whether or not the problems are solvable or where the problem is. So you can see our general workflow here. We start with two inputted database schemas that we want to match. We do that via Valentine, where we will get some possible matches back. Afterwards, we try to convert these possible matches into quantum suitable input. We do that with the stable matching problem, also known as the stable marriage problem, and QUBO. Out of both of them results the stable matching QUBO formula that we can input into the quantum computer. We then try to compute the best solution on the real or simulated quantum computer, and then after we achieved these results, we check whether the solutions are viable or not and give them back to the user. I will now explain the workflow on the basis of a Jupyter Notebook, which executes a simple example. So let's dive right into the Jupyter Notebook. In step 1, we have to input two schemas. We input a schema A, being here phone name number, and a schema B, being phone last name and first name, as you can see here. In the second step, we have to select a Valentine matcher. More information regarding the Valentine matches can be found on the link. You can see it here. Out of all these Valentine matchers, we can select one. In our case, for the Jupyter Notebook, Coma, Cupid, or Similarity Flooding are decent. Therefore, we select one of these three. In step 3, Valentine will match the two inputted database schemas with the selected matcher. The closer the value towards 1, the better the match is. If we look onto the output of the Valentine, we see here the schema A candidates that got a possible match, and we see here the schema B candidates that got a possible match. So in this case, we have the matching phone with a value of 1, we have name last name with a value of 0.91, and we have name first name with the same value 0.91, and we have name and phone with a value of 0.87. All of these are possible matching pairs. Afterwards, we create preference lists out of the matching score of Valentine. What we do is we take schema A candidate phone, see how often it appears here, and then we take the corresponding schema B candidate. So for phone, we have one schema B candidate phone, so phone has only the preference phone. For name, it appears 3 times and it has 3 possible matches, last name, first name, and phone, and therefore we write its preference list last name, first name, and phone on the second position. We can also check it here. So for name, we have the preference list last name, first name, and phone on the second position, since last name and first name are always preferred over phone. We do the same for the schema B candidates. So we check how often phone appears here. We have phone once, phone twice. So we have 2 possible matches for phone, and therefore its preference list is phone on the first position, since 1 is greater than name on the second position. We do that for our last name and first name as well. Our final preference lists are for phone of schema A, phone, for name of schema A, last name, first name, and phone. For schema B phone, we have phone name as its preference list. For our last name, we have name, and for first name, we have also name. We can also build the possible pairs. So we have phone, phone as a possible pair. We have name, phone as a possible pair. We have name, last name as a possible pair. And we have name, first name as a possible pair. So we can see that we have here 4 possible pairs in total. Next, we will have to select a global matching algorithm. In our case, we chose the stable matching, also known as the stable marriage problem. We then have to see how we get the stable matching problem onto a quantum computer. Therefore, we selected QUBO. QUBO is basically a quantum algorithm that makes the stable matching problem solvable on the quantum computer. The corresponding QUBO formula is shown in the picture of step 7. So we have here the first part of the QUBO formula, the second part of the QUBO formula, and the third part of the QUBO formula. The first part corresponds to the objective function being find as many pairs as possible. The second part counts for all possible pairs. So we do this 4 times in our current example. It stands for the stable constraint, so we try to promote pairs that are not blocking and will add penalties to pairs that are blocking. The third part stands for the constraint that no one is matched twice, that we have only monogam pairs in the end. For this formula, we can also set the penalties. So we have here penalty P1, penalty P2, and penalty P3. And we can individually set them. Normally, they're set to P1 being 1, P2 being the length of the A candidates. So in this case, it's 2, since we have phone and name as possible matching candidates of A after the Valentine matches. And P3 is P2 times P2 plus P1. You can also edit them individually if you want to try other penalties. After this, we will insert our possible pairs into the QUBO formula from before, and we also insert the penalties. And then we get our final QUBO formula being this term here. And we can see that we have 4 binary variables which represent our 4 possible pairs. It can also be said already that each of these binary variables will be 1 logical qubit in the quantum computer. Afterwards, we will try to find solutions on the simulator, gate-based quantum computer, or quantum ALINA. The simulator we will use is the IBM Q Quasant simulator, which has 32 qubits. For the gate-based quantum computer, we will use the IBM Q Lima, which has 5 qubits. And for the quantum annealer, we use the Advantage System 4.1, which has 5,627 qubits. At first, we will execute the simulator. If you want to have more information regarding the simulators, you can click on this link. We have multiple possible solutions that we achieved from the simulator. We can see the matches that appeared in the final results. So in this case, phone, phone, and name, last name would get matched in the final result with a QUBO value of -10. The encoding shows which possible pairs are present. It acts the same way as our possible pairs before, so the first position would in this case always refer to the pair phone, phone. The second position would refer to the pair name, phone. The third position would refer to the pair name, last name. And the fourth position would refer to the pair name, first name. Whenever they are 1, they exist in the current solution. After we got the results, we can also try to plot them to see how the probabilities are along the values. We have on the bottom the solution values, so the QUBO values. On the left side, the probability distribution. And we have for every bar also the corresponding encoding. We can also try to solve the QUBO formula on a gate-based quantum computer. We do that on the IBM Q Lima. Again, more information can be found on this link. So here we basically get some of the same results as before, and we again can plot it. So after we saw the simulator and the gate-based quantum computer, we can also try to solve it on a quantum annealer, in our case the Advantage System 4.1. Here more information can be found on the second link, and I also have to say that we used some pre-implemented things from the CubeMX SMTI program, which is a paper that can be found at this link. It's the same paper that we used for our Cube formula. So for D-Wave, we also get some results back, and we will also plot them once again. At last, we want to validate the correctness of the solutions that we got back, and we will do that again for the simulator, the gate-based quantum computer, and the quantum annealer. Note that this will happen on the normal CPU again and not on the quantum computer. So for the simulator, we get the first 3 results back. So in this case, we have 2 times -10, 2 times -7, and 5, which are all valid results. For the gate-based simulator, we basically get the same results back. And for the quantum annealer, it only founds the -10, -10, and the -7, -7. This concludes our demo. What did we achieve? Well, we did realize an end-to-end solution as a hybrid algorithm, which is part of some classical and some quantum hardware. We did also achieve a demo where every step can get executed and each different intermediate result can be inspected. In the demo, you can also change multiple inputs like the schemas, the Valentine matcher, the penalties, the QPUs, and see for every input how it affects the outcome of the matching. Thank you for listening to my presentation and enjoy our paper.